Alright, so welcome to my second video of Unit 20. Um, Basically, in the last video, what we covered is basically SN2 reaction mechanisms. So SN2 reaction mechanisms, right? We had substitution, then nucleophilic, the N, and the 2 is bimolecular. So what implications that had in the last video, right, is that the rate was determined by basically two different molecules. So the rate is equal to the rate constant times the concentration of the nucleophile multiplied by the concentration of the haloalkane. So this is just a quick review of the last video. We also said that SN2 mechanisms typically they're for primary carbons, which means that basically you take your halogen, you take any halogen, chlorine, you bond it to a carbon, and it depends how many carbons this carbon is bonded to. If it's only bonded, if it's like an alkane chain, we bond it to one other carbon, and then the chain can continue that way. We don't really care. But that means that this carbon is bonded to a hydrogen up here and a hydrogen down there. So since he's bonded to only one other carbon, we say that this is a primary carbon. If we were to make it, a secondary carbon in this case, this carbon right here that the halogen is bonded to would need to be bonded to two different carbons. We'd have a carbon, a CH3, a methyl group up here, or some sort of longer carbon chain. So now you can see he's bonded to 1, 2. So we say right now he's a secondary carbon. And then finally, if we wanted to make our tertiary carbon, just because I think my last video I didn't describe this as well as I should have. A tertiary carbon, you put a methyl group up at the top, you put a methyl group down here at the bottom, and now the halogen is bonded to a central carbon, which is bonded to 1, 2, 3 different carbons. So this is a tertiary carbon. And these are the ones that we're going to be working on today. But basically for our first one, we talked about nucleophilic substitution, in the SN2 mechanism. And that was primary carbons. So what that means is, you take your carbon, and right, we've got a few different, we've got that tetrahedral structure. Carbon's bonded, in this case, to 4 different groups. So it's got a tetrahedral structure. We'll just say H. I'll draw this going back as an H. One coming up here as our halogen, and then going to the right for a carbon. And then to continue the chain, it doesn't really matter. This will be a CH2, and then continuing the chain. So when we talked about SN2 mechanisms, what happens is, right, this is tetrahedral. It might not look that way, but I tried to draw a tetrahedral. What tetrahedral was basically, you got your central atom. You should have done this in Unit 4, hopefully. You've got one hydrogen, one group that comes out, one group that goes into the back, one group that comes out to the side. I'll just keep doing H's. We'll just do like methane right now. And one group that comes out of the top. So basically, if you imagined, right, the bond angle, like you should hopefully know, between all of these different groups is about 109.5. So the bond angle between this group and up here is 109.5. This hydrogen group to this hydrogen group is 109.5. This hydrogen group back around to the back hydrogen group is 109.5. So no matter what, we've got bond angles of 109.5. So what this should say is it's symmetrical in every single way. The way that I drew it here doesn't really look symmetrical, right? It doesn't look tetrahedral in every domain because this group right here isn't coming down. But if you look at these 3 groups, right, they're coming out 3 to the bottom like we have here and 1 to the top. So you just need to basically practice changing these shapes around in your mind. So what we had talked about with our SN2 mechanisms as we had talked about in a stereo inversion, um, and we'll talk about that in a second. So basically, we had an inversion during this reaction, and the type of inversion that we call it is called a Walden conversion, which means an inversion at the stereo center. And the stereo center is this main carbon here. So what's going to occur is let's pretend we had a reaction here. Let's pretend we have, a basic solution with hydroxide ions floating around in it. So we've got 1, 2, 3, 4, 5, 6. So now that's our hydroxide group. So what's going to occur is that if you can kind of imagine it, like we had said in that last class during Sn2 mechanisms, it always attacks from the back side. So wherever basically your leaving group is right now, it's the halogens or our leaving groups that we're studying. It always attacks from the back side. So it attacks from this big gap here. Let me try to change the color. It attacks through this big gap right here. There's kind of like, if you looked at the bottom, let's draw out a molecule that's tetrahedral. And if you take your eye and you look at this molecule from the bottom, what you're going to see is you're going to see the center. You're going to see one group out here, one group out here, and one group out here. So this is looking at it from the bottom. And then this one is superimposed on top of another one. That's the one that points to the top. There's another one hidden behind the back up here. Hidden behind the back up there. So basically, you've got all of this space between these atoms in order to come in and attack. And that's why it always attacks from the backside. It's got a massive opening right here, right? There's 109.5 degrees between all of these, but we've got a nice circle right in the middle that we can attack from. So what ends up occurring is that this hydroxide comes in. It's a nucleophile. It wants to attack a positively charged nucleus. And we've got chlorine right here, which is electronegative, and carbon here, which in this case is electropositive. So it wants to attack a center. This center is positively charged. It's negatively charged, and it has the electrons it needs to form a dative covalent bond. So what it does is it comes in and it donates its electrons up to this carbon. And this carbon, chlorine finally is like, yes, finally I can, it's electronegative. It wants electrons. It's stable with more electrons. It's happy with them. So it can take the electrons from the carbon bond because it's formed another one. But this is the one thing I kind of wanted to point out to you guys, is that we do have this Walden inversion, Walden conversion, I like to say inversion. So what occurs, right, if this chlorine leaves, let me just kind of erase this off here, and you imagine the chlorine is just, having the time of his life over here, right? He's got the disco ball, he's really living it up, he's happy. But if you look at this, right, carbon with 4 bonds, even though it's a dative bond coming from the hydroxide, still maintains that tetrahedral structure, right? But it's lost that tetrahedral. Now it looks more like a pyramidal structure. So in this case, what occurs is that these bonds shift. They shift to go back into that tetrahedral structure. So instead of coming out to the bottom now, let me kind of change the color a little bit. Instead of coming out the bottom here now, he shifts to start coming out of the top. Instead of going back on the bottom here, he goes back on the top. And this guy, since he's just to the side, is just to the side. He stays to the side. He will invert too, but not in my picture. If we wanted to draw him inverted, I can basically just draw another CR group up here, erase off the old groups, and then this hydroxide is the new group that's coming out of the top. So if we were to draw that bond, we'd just say a hydroxide coming out. And now you can see we've maintained, right? We've maintained that tetrahedral structure from before, whereas tetrahedral coming out the side. Now it's inverted. What was going down before is going up. Going down before is going up. And what was going to the side before is also going up. So basically, we've changed the inversion. The way that I like to think about it, and the way that your book describes it, is it's kind of like an umbrella, right? Umbrella in a snowstorm, or a snowstorm. Oh my God! If you're using an umbrella in a snowstorm, that's not too good. Okay, so it's like an umbrella, right? There's a gust of wind, and this gust of wind takes your umbrella and it flips it. And that's exactly what this does when it comes in. Now your umbrella, is functioning, instead of repelling rain, it's acting as a big cup for rain. So it's inverted that umbrella, and it's the exact same thing during an Sn2 substitution reaction. Is that it inverts the center. And this is going to get important by the end of this unit, where we're looking at chiral centers, carbon bonded to 4 different groups. And depending on whether it's an R or an S version, it's going to make a difference. So we're going to talk about that a little bit more later. So this video is basically mainly just to clarify my Sn2 reaction mechanisms. And in the next video, we're going to talk about Sn1. So make sure to join in for the next video, and hopefully this was useful. Thanks.